Hello, this video is a recording of my original conference talk given at the AI and Big Data Expo Europe in Amsterdam in October 2024. In this video, we'll introduce CrateDB by looking at some renewable energy data, specifically data from UK offshore wind farms. My name's Simon Prickett. I'm the Senior Product Evangelist or Developer Relations Engineer at CrateDB. I'm based in Nottingham in England. So let's begin by looking at what CrateDB actually is. So for those of you who haven't heard of it, CrateDB is a hyper-fast open source database that's optimized for real-time analytics and hybrid search. We'll be looking into what that really means in this talk, but for now, you should know that CrateDB is a place to store your structured, semi-structured, and unstructured data. It has dynamic and flexible schemas. So that means that data is stored in tables. Tables can have as much or as little schema as you need. And those schemas can expand with your data or be fixed if you know what your data looks like. Moving on from that, there's an advanced indexing. So this means that everything is indexed by default, which is ideal for an analytical database. You're going to put data in there. You might not necessarily know when you store that data and design your database what sort of queries are going to be made of it. So by indexing everything by default, including when that schema changes automatically due to its dynamic and flexible nature, you can ensure that queries are always going to hit an index and will be fast. So how do you get the data in CrateDB? It uses a standard SQL interface, so something that you're already familiar with. And it's Postgres wire compatible. This means that you can use tools and ecosystems that you're already using. It's also optimized for a high volume of concurrent reads and writes at the same time. So ideal for situations where streaming data arrives, it's constantly in flux, it's never going to end, and you want to perform some sort of analysis and aggregation over it to make sense of it. How does CrateDB fit into what we see as the sort of database challenges of the modern world? Well, imagine you're building an application, and you might start out with a regular SQL relational database management system, and that's a great choice, and it allows you to store data in tables and query them with SQL and use ecosystems that you're already familiar with. As times move on, you might find that you need to perform some more sort of search type queries. So in order to do this, you might consider adding a search product, replicating some of that data from your SQL database into your search product. And now your application is working with a couple of things. It's got the SQL database and SQL for storing and querying data. And some types of queries, you're going to use the search engine, and it's probably going to have its own query language. So something that's different from SQL. As we move on, you might find that your data needs expand and your application or your enterprise has a need for time series data, which is increasingly common these days, and also document or less structured data, so sort of JSON type things that may have optional pieces to their structure or may have very, very different structures inside the same document for the same collection or concept. So by this point, you've got quite a few things going on here. You've got multiple different query languages or dialects, and you're managing quite a bit of operations and data replication. Before you even consider something like, oh, we might want geospatial data, and some databases handle that better than others. You might end up with a specific geospatial store for that. And similarly for vector data for your AI models, so to store your embeddings with. So things get quite complicated at this point. And what we aim to do here at CrateDB is solve that by providing a single place where all of those types of data can live together in a single table if necessary, and can be accessed through SQL, so standardize that query and ingestion language. The database itself supports all of these different data types, so regular tables, JSON documents, which are in tables in CrateDB, time series data, full text vector. We have a float vector type that we'll look at later in this talk, and also geospatial for storing where things are and being able to query what things are within a certain area or what areas do I pass through. We also store blob data, but that's not the focus of this talk. The database itself is designed, as I said, for high volume concurrent reads and writes. It scales easily using commodity hardware or in our cloud. You can add additional nodes. Nodes don't have specific roles. The cluster will figure that out for you. And you can deploy CrateDB on the edge, so something like a Raspberry Pi, or in many, many places around your network. You can have a hybrid or on-premise solution, and you can have a public or private cloud. So we operate a cloud system that you can log into and provision a database on Azure or Google Cloud or AWS. And you can also go to those cloud marketplaces and find CrateDB there. So for the remainder of this talk, we're going to look at a specific example. So we're going to be working with some offshore wind farm data from the UK. Why did we pick this? Well, wind power is kind of becoming a really big thing. The UK is starting to get out of other forms of less clean power. So on the day that I went to Amsterdam to deliver this talk in person, it was the last day that the last coal-fired power station in the UK was scheduled to operate. That also happens to be right near where I live, so I passed it on the way to the talk on its last day of operation. Over on the left there, you see a map of the UK, and we currently have 45 offshore wind farms and a number that are onshore as well. So this talk, the data set concentrates on the offshore wind farms. The data comes from something called the Crown Estate, which manages and licenses those and gathers data from them, but doesn't itself operate them. They're operated by private operators. Over on the right there is a pie chart of the makeup of the UK's electricity generation for whatever specific time I happen to pull the data for. And at that point, you can see that wind was making up 22-23% of the overall generation mix. This is only going to grow as things move forward. And as wind farms deliver quite a lot of data, the amount of data here is going to grow. It's also a never-ending stream of data. So, the wind doesn't end. The wind farms will operate for some lengthy period of time, and we're always going to be getting new information from them. The value of that information on its own isn't that high, but aggregations and trend information is really important. So that's why I picked this as an example to show CrateDB as a real-time analytics type database. We have a couple of sources of data going on here. So for the wind farms themselves, so an organization of turbines in a given place, we have a JSON document that describes the name of the wind farm, a physical location that it is in two ways. So we have a singular point for, here's a point on the map that you can consider North Hoyle Wind Farm, in this case, to be here. And then we have a geopolygon of its boundaries. So if we were to draw on the map the outer edges of the wind farm, for example, for telling shipping to avoid it, we can do that with that information. For each of the turbines in the wind farm, we have a location, and that's inside an object, inside an array there. So there's an object turbines, there's an array locations. Inside that is a geo point for each turbine. And then we have some free text information that describes the wind farm. So it might discuss the original planning permission, the history of when it was built, who built it, what size it is, what position it was built in, as in, this one was one of the first ones to be built? Was it a more recent one? And any other local information. It's basically free text. So we have this information for each of the wind farms, and there's 45 of those. This doesn't change very much at all. So this is essentially sort of standing data of, it's a wind farm. We're only going to change this whenever we add a turbine, delete a turbine, move a turbine around, or create a new whole wind farm. So let's look at that on the map. So North Hoyle here, its polygon is pretty much rectangular. It looks like this. And if we zoom in on that, we can then, with the data we've got, plot the position of each of the turbines. So you can find that they're in a nice set of lines there out in the ocean. So North Hoyle is just west of Liverpool. It's off the coast of Wales. How do we model this in CrateDB? So I've chosen to have a table for the wind farms, and we're going to create a table there with a pretty standard looking SQL statement. And we're going to model each of the things in the document on the right in the table schema on the left. So I won't go through all of these, but we'll pick out a couple of interesting ones. So first up, let's look at boundaries, which is the geopolygon. So in CrateDB, we're going to model that as a geoshape, and we're going to index it with a geohash index, which will allow us to do fast queries against positions. So we can say, is something inside this shape? Does this shape intersect with other shapes? And so forth. And we'll see how to use that later. So that's a geospatial example. Inside the same table, I've got a field called turbines. That has an object dynamic type. So that basically tells CrateDB to expect an object there. And by dynamic, we mean the schema isn't necessarily fixed. So here I'm describing a bit of the schema for this object. We're expecting a model for the turbines, and that'll be text. We're expecting an array of geopoints in there for the locations of the turbines. And we're expecting a number for how many turbines there are. We could add more stuff into this later, and if we put a document in there that had additional fields, CrateDB will automatically expand the schema to include those and index them from that point onwards. So finally, the fields that I wanted to bring your attention to are description and description_vec up the top there. So again, inside the same table with geospatial data and object document style data, we have a text field that is indexed using full text. This tells CrateDB to build a full text search index over this field, and CrateDB uses Lucene for that, so something that you're probably already familiar with. And again, it can be queried with SQL. So here we're going to be able to do sort of keyword matching type questions and answer things that involve fuzzy logic. Underneath there, we have a description vec field that is of type float vector. So I've said here it's going to be a vector with 2048 dimensions. And how do we get that data from the description text that we're given? What we did was we ran that data through an OpenAI text model and told it we wanted 2048 dimensions back from it. And it generated a large string of numbers that represents that are meaningful to it. And we stored them inside CrateDB in a float vector column. Inside the database itself, we can then perform KNN or nearest neighbor semantic search on those fields. So we can encode a search query using the same OpenAI model. So we might ask a question like, which wind farms are located in the southeast of England or have certain properties? And we can answer that using semantic search by doing a KNN search between the encoded version of that query, so the vector that represents the query, and the vector that we've stored in the database. We could also compare wind farm descriptions to see which wind farms sound like other wind farms from their textual descriptions by doing that same KNN search against description vectors on multiple records in this wind farms table. Moving along, we have a second sort of data. So we have data about power generation. So the wind farms themselves, there's 45 of those. They don't change very often. They don't move around very often. But what they are doing constantly is outputting power. So 24 hours a day, 7 days a week, some or all of the turbines, unless they're in maintenance or it's becalmed, there isn't enough wind, will be generating power. Once an hour, the Crown Estate generates an output document from each of these wind farms that has a few fields in it. So we can see a couple of examples of those over to the right. what we see is each wind farm has got a wind farm ID that tells us which specific farm the data comes from. We've got a timestamp that tells us which hour the time is for. That's a Unix millisecond timestamp. We've got an output, how many megawatts the farm was outputting at the time. So that's all of the turbines combined. We don't get data for individual turbines at this point. And we've got a percentage, which is what output of its total capability is the wind farm generating at this point. So up at the top there, you see it was running at 29% of its possible output capability. So these records, we get 45 of them every hour, one for each wind farm, and they'll continue all the time. They'll never end. So this is a source of streaming data in that it has no defined end point. You know, if we got out of wind power, things would end. But for now, we're going to assume that this will continue forever. How do we model that in CrateDB? Well, I've created a second table here that we've chosen to call wind farm output. And there's a couple of things that we'll look at here. So we're going to look at how we manage the data in it and also how we model the data in it. As you can see, it's again a SQL create table statement. It's fairly standard stuff. We have one of the documents on the right, fields on the left. So we're going to store the wind farm ID as text and a timestamp as a timestamp, as you might expect. And then we'll skip over that a minute, and the output will store as a double precision number, and same with the output percentage. But I've also added another field in there. So there's a generated field in there that the database itself will build for us when we insert a record. And what we've said is I want that to be called month, and I want it to be generated by truncating the value of the timestamp, so the current hour that the record is for, back to the nearest month boundary. So if the timestamp was for some time on, say, the 7th of October, we would truncate that back to the first hour in the 1st of October. And we're going to use that for aggregation. We're also going to use it for data management. So how we're going to use that for data management is we're going to partition the table by that field. So you'll see that down the bottom, partitioned by month. And what that means is the database is going to create a series of sort of virtual subtables that contain only 1 month's worth of data. And then the actual table, wind farm output, will be an amalgamation of all of those. How does that help? Well, it means that the database engine, when it's querying things in a time series, will know where data for certain parts of the time series lives and can only consider the right partitions straight away without having to do much work. It also helps us because this is a source of data that will continue forever. So there's no end to this. We're storing it in a database, which means we're using storage. Storage is finite, and eventually we'll want to remove some of this data or archive it because either it's not relevant anymore, or it's not used enough in queries, or we'll only want to bring it back at certain times when it is. And partitioning the table like that allows us to manage that data accordingly. So once we've got the data in the database, which is just achieved by standard SQL insert statements or other sorts of bulk loading process. Again, CrateDB is Postgres compatible, so we could write some code that uses a Postgres driver to put data in there, or we could use other tools, or we could sync this up to a streaming source such as Apache Kafka. So let's assume we've got data flowing into the database. We're going to want to query it. There's nothing particularly special about this query on the screen. All we're doing is selecting a few fields from the wind farm output table, so the time series type one, for a given wind farm, so North Hoyle 1, and at times where the output percentage of the wind farm was at least 50%. So we're basically looking here at the last 5 times that the North Hoyle wind farm output more than 50%. And you can see there the times, the output, and the output percentage. Nothing particularly special here. The aim here is to demonstrate that you can use standard SQL queries with CrateDB. I said earlier that with this wind farm output data, so the time series one, the value of individual records isn't that high, but the value of an aggregation or a trend over these records is much more of interest to us. So aggregations are something that we're going to want to do a lot with the time series. So here's an example that shows a simple aggregation, but also shows that we can do joins across tables in CrateDB, as you might expect. So here what we're doing is we are getting the average output percentage for each wind farm by calculating that with the average function. I'm then truncating it down to a couple of decimal places so we don't get very long numbers. And what we're doing is saying we want those for the time period where the month matches a certain timestamp. So that field that we created that was auto-generated, so that timestamp might represent September or October. And what we're doing is we're joining that information with the nice name from the wind farm from the wind farms table. So rather than getting the little code names that you see in the time series data, we're getting the proper names, so Seagreen Phase 1, etc. And again, we're just ordering those. And what we see is the highest average output percentage in this time period was Seagreen Phase 1. So moving along, we quite often also want to take a step back from the data. So we've got hourly data at the minute. We might want to look at larger time periods, so a week, a month, a year, etc. So rather than seeing this forest of individual data items, we might want to take a step back and look at the bigger picture. We can do that in CrateDB with downsampling, which is a technique that is supported by a function called dateBin. So what we're doing here is saying, let's take the timestamps and group them into weeks. So we're saying I want every data point within the week of the timestamp field to be considered as a single bucket. And then what we're doing is running an average function over that bucket and getting the hourly average output for that week. So again, we can sort of step back from the hourly data and start to see week on week how North Hoyle was performing in this case. And again, this is a slightly more advanced SQL query that shows you that CrateDB supports a lot of standard SQL functions. It's very rich. So we can do window function here. And the purpose of this is to create a sort of aggregate sum. So for each hour of the day here, we're outputting what the hourly output of one of the wind farms was. And then we're calculating a running total for how much or what the total output for the day so far is from that wind farm. So you see that output day so far column on the right becomes the sum of the current record and everyone that's preceded it that day. So we're doing that with a SQL window function, which is built into CrateDB. And again, you can expect these sorts of queries to be very, very fast because everything's indexed by default. We use a column of storage for these columns, and the table's partitioned so we know when the timestamps, which partitions they fit into. We can only consider those. We had some geospatial data in there and we've kind of ignored that so far. So now it's time to take a look at how that works in CrateDB. With wind farms, they don't move around very much at all. So they're rooted to the ocean floor generally. Some of them are out there on boats, but those tend to be small or are experimental. And equally, they don't necessarily move around that much. So why do we want geospatial data at all? Well, a couple of reasons. We might want it for planning purposes. Where do we put new wind farms? How do we plan other things around the wind farms? And also stuff like shipping. For example, we'll want to plot routes that avoids these. So knowing where they are is really useful. we might want to ask questions like, given this area on the map here that we've drawn, well, what's going on with wind farms in this area? So we don't know which wind farms are in that area. We need the database to be able to tell us that, so we can then perform some sort of queries or aggregations on the data represented by those wind farms. In order to do a query like that, we need to define here in a way that the database can understand. There's a couple of standard ways of doing this. So what we're looking at here is GeoJSON. It's a JSON document and format that describes geospatial relations. So here we have a polygon. A polygon's consisted of an array of coordinates. You can actually have multiple polygons in the polygon, at which point becomes what's called a multi-polygon. For example, if you've got an area with a hole in the middle, or an area of land that also is linked to an island somehow. Here we've got a simple polygon that's a series of points off the coast of the UK. How do we use that in CrateDB? Well, we query everything with SQL, so it's going to be a SQL statement again. And CrateDB has functions in it that understand geospatial data. So here we're saying, I want to find some things out about wind farms whose location, which in the database was a given geo point, is within, so we're using the within function there, the polygon described by our GeoJSON. Now, we don't actually have to change the GeoJSON to put it into a database query. We just put it in there verbatim, and it can be generated by most mapping libraries. So it's very easy to draw out an area on a map and ask the database a question about it without having to marshal data into and out of different formats. So here we're asking the database for the names and the latest output percentage from wind farms that fall within our polygon. Also to note, I'm using a function there called maxBy. So that's a CrateDB function, and what it does is it tells us the maximum, or it tells us the value of one field at the point at which another field is at its maximum. So to get the latest output percent here, I'm saying I want the value of output percentage at the point at which TS, the timestamp, is at its maximum. And then we're going to combine that in the same query with this geo filter that says, and the wind farm has to be within the polygon that we are describing. Here you see the results of that. So we have a number of wind farms that match and their data. I've chosen to plot the wind farms here using their individual points. Because we have the boundary information, we could also plot the boundaries of the wind farm on the map instead. Moving along from geospatial, we also had a field inside our wind farms table that I said we were indexing with full text search using Lucene. So here we have some text as an example, so descriptive text about North Hoyle wind farm, and we've indexed it using full text, which means that we can do different sorts of searches against it. So in order to perform these searches, we use the match predicate or match function. And again, it's inside a standard SQL query, so we don't have to go learn some other dialect for this. So we're combining this with other SQL clauses too. So here I'm asking the database to find me the name and the number of turbines, which is in an object. So I'm using the square braces notification there to access a field in an object. And the description text from the wind farm table for wind farms where the description matches the keyword oil or gas in any order. So this is standard Lucene syntax. We could do oil and gas in that order, or anything more complicated that we wanted to do. But for now, we'll do oil or gas. And we also want there to be at least 80 turbines in the wind farm. And we want our result set back with the wind farm having the highest number of turbines first. So here you'll see we have got 3 example results. And the first one matched because it talks about vegetable oil. So that's a match on the oil keyword. The second one, natural gas. And the third one talks about both oil and gas. So we can do keyword type searches. This is Lucene underneath, so you can do fuzzy search with slop and all of the things that you're used to with Lucene. Now, you'll hear a lot of database companies talk about vector similarity as well. And earlier in this talk, I said that we created a vector representation of our descriptions using an OpenAI text model. So what that comes out as is a series of numbers that we've stored in CrateDB. It's got a native float vector type. And those vectors can live in tables alongside all of the other types of data. So in our wind farms table, we have vector data, we have geospatial data, we have object data with a flexible schema, and we have regular stuff like numeric and text. So how do we query that? We have a function KNN match, so nearest neighbor match. And in order to query that, we have to provide a query vector. So to get that, we have to take our query, in this case text, but we could be comparing all sorts of different types of different types of data. It could be image data, for example. As long as we've got a vector representation of it that's from the same model that was used when we stored the vector representations of the data, we can do a query and see which records in the database are nearest semantically to our query. So here we're asking something about Southern England. Where are which of the wind farms in Southern England? We could have used the geo for this, but for the purposes of this demo, we're using vector similarity. So it's going to look at the text, but it's going to look at it semantically and in a way that keyword search wouldn't necessarily have got to the same results. So you can compare and contrast the two methods. You can also combine them in their own query. So here, for example, query results include things that talk about the southern area of the East Anglia zone. A keyword match wouldn't have known that that was in southeast England necessarily. Sandbanks off the coast of Suffolk, same, it wouldn't have known that without this greater semantic level that the AI model gives us. Once we've done all of our designing of our database and got all our data pulled in and got some queries, then chances are we're going to want to do something visual with them. So wind farm data is inherently really about maps and graphs and trends and things. How does that work with CrateDB? Well, recall that I said that CrateDB uses both SQL and the Postgres wire protocol. That means it slots into a wide ecosystem of tools and other things that allow you to get data in, get data out, visualize it, and manage it. Here we're using Grafana, so we've got a very simple Grafana dashboard. It's powered by some very simple SQL queries, and it's connected to CrateDB using the standard built-in Postgres driver that Grafana comes with. So we don't need to do anything special or build any software. Expanding on that, you can see that CrateDB fits into a wide range of tools and programming frameworks and use cases because of the support for native SQL, near real-time analytics, and fast indexing. You can use it for things like training a model or inferences or a RAG pipeline with things that you're already familiar with, so maybe LangChain. If you're pulling in streaming data, you can either just write code that puts the data in there using a Postgres driver, or, as is more likely, you might have an existing streaming data source such as Kafka or Flink, and you can pull data in from there too. Again, standardization of SQL and Postgres protocol greatly helps with this. And as we come towards the end of this talk, I work in developer relations, so I would love for you to learn more about the product. If I can leave you with one thing, it would be go to our academy at learn.cratedb.com. The academy is an online training portal. Everything's delivered through videos, cloud databases, and sample data in the cloud. On our fundamentals course, you'll learn about CrateDB, you'll learn about all of the different aspects of it. So geospatial, full text search, vector similarity search, how it fits into an ecosystem, and how to model data. You'll do all of that using a standard data set, which is open data from the city of Chicago. So it's real world stuff that you can actually interact with. You can put it on a map as part of the course. You can see how aggregations work, and you can try that out entirely in the cloud with quite a large data set of hundreds of thousands of records. If you complete our multiple choice exam at the end, which is open book, you can refer to the course materials or the internet and take as long as you need. Then you can earn a certificate of completion that you can put on your LinkedIn profile. And that was all I had for you today. So thank you very much. If you have any questions about CrateDB, come find me online. I'm easy to find, or join our community at cratedb.com. Thank you.